Good afternoon, all. This is Cassie Powers with NASEO. We're going to go ahead and get started. So welcome and thank you for joining us in the third of our discussion series, Powering Up Data Centers. This particular webinar is going to focus on tools to meet data center growth and energy demand growth. I'm going to share a little bit about NASEO for those who may be new to us, and then we'll get into a little bit of background on the discussion series before we turn it over to our esteemed moderator and panelists. And so NASEO, we are the National Association of State Energy Officials. We're the national organization representing the governor-designated energy offices in each of the states and territories. And we help to advocate on behalf of the energy offices with the Department of Energy and with Congress and help to elevate concerns, challenges, and successes from the states. We also host a series of convenings and conferences, et cetera, so that state energy offices can connect with peers as well as with experts. And we also have a research and an analytical arm to support state energy offices in really energy policy planning or program development that they may do. So the data center series that we have been hosting over the last few weeks is really focusing on trying to figure out how much power is needed and what tools and resources states may use so that they can ensure that data centers get the power that they need to serve their customers. This particular series is going to explore strategies that energy offices can use to address growing data center electricity demand while supporting energy affordability and grid reliability. And the goal of the discussion series is twofold. It's to ensure that states are better equipped to develop policies and programs to meet the energy needs in their states, as well as propel economic development and maintain affordable energy for customers. And it's also to enhance states' understanding of some of the challenges as well as the opportunities associated with these new sources of load. So far, we've held two of our webinars. The first, Data Centers and the Energy Landscape, provided perspectives on various facets of data centers and their role in the U.S. energy landscape. And then the second was focused on planning and siting considerations for data center power. And this explored the challenges and opportunities of planning for as well as siting data centers from a number of perspectives, including innovative partnerships and approaches. And both of the recordings are available on our website if you had missed them, and we can drop a link to those in the chat. We also plan on hosting a couple of future conversations or webinars, one on balancing state affordability, reliability, and the security of the grid, and then another on co-location considerations. And we'll likely also explore then some of the technological developments. For those who are attending the NASEO regional meetings over the next few weeks, you'll also likely hear quite a bit of discussion around the intense amount of energy demand as well as the supply needs for the data centers and other load growth. And so we would also just like to say that we would welcome your input into topic ideas, so you can feel free to reach out to any of the NASEO team if you wanted to flag topics for future discussions. A couple of housekeeping notes that I wanted to flag. One is we are, of course, in a Zoom and the webinar format, and so only speakers and panelists will have camera and mic access. Also note that following presentations and the discussions will have the opportunity for audience Q&A, and you can use the chat function to pose your questions at the bottom of your screen. And then also just to note that this webinar is being recorded and will be posted to the NASEO website. And so now turning to the agenda overview, onto the good stuff. And so first we'll hear from our moderator, Alexa Wojtek, the Deputy Director of the Office of Energy Programs at the Tennessee Department of Environment and Conservation. Alexa is going to provide some opening remarks as well as share the perspective from Tennessee, one of the many states, of course, facing a number of policy and programmatic decisions regarding the data center growth. Next, we'll hear from Karsten Baumann, the Director of Strategic Initiatives and the Solution Architect at Schneider Electric, who will detail how data centers can function as flexible grid resources and provide an overview of Schneider's smart IT infrastructure. Following Carson's presentation, we'll hear from Anucha Rachniake, the Emerging Technologies Executive at Electric Power Research Institute, or EPRI, who will provide an overview of EPRI's DC Flex initiative and detailing the collaborative effort focused on how data centers can support and stabilize the electric grid while improving interconnection and efficiency. And then our final speaker will be Hillary Pearson, the Vice President of Policy and External Affairs at Line Vision, who's going to cover how monitoring and optimization technology can help identify additional grid capacity for large loads and the data centers. And so we have a packed agenda, lots to cover. I know we are asking for an hour and a half of your time. Again, feel free to use the chat to pose questions, etc. And with that, I'm going to turn it over to Alexa to get us started. Alexa?
Thank you, Cassie. And thank you guys for the opportunity to be with you today. I'm excited to learn from our speakers who I'll be passing it to in just a couple minutes. As Cassie mentioned, my name is Alexa Wojtek, and I'm a Deputy Director of Programs at the Tennessee State Energy Office. Tennessee, like many other states, is currently no stranger to the uptick in interest and development of large-scale data centers to support AI and other high-performance computing needs. Data centers, they are complex beasts because, there are many things all at once pertaining to energy, water, land, economic development, and so forth. From my perspective, it seems that over the last few years, or initially at least, many states didn't seem too keen on attracting data centers, given how energy and water intensive they were, and the fact that they didn't seem to be creating as many jobs as perhaps some other types of economic development opportunities. However, it does seem that recent discussions have shifted perspectives, highlighting how some of these hyperscale data centers can have a positive impact on a local economy, particularly due to increased tax revenue that they can generate and how such could be reinvested into local infrastructure improvements. There's also increasing conversation on how storing and processing data within the US rather than in other countries like China is crucial for several reasons, including legal security and other economic considerations. In recent years and even months, Tennessee has seen a number of entrants into this space, including Meta, formerly Facebook, announcing the creation of a data center campus in Gallatin, just outside of Nashville, Tennessee, as well as Elon Musk's xAI data center in Memphis, which has recently been in the news due to its use of natural gas generators to sidestep electricity supply constraints as the data center works out its power supply agreements with the local utilities. From an energy perspective, data centers, they seem like they could either be the best thing or the worst thing for electric grid growth in the next decade, depending on how we develop these sites and these data centers. And so, we've heard recently the new energy secretary describing this issue as the Manhattan Project of our time. As both psychologists and U-Haul drivers like to say, there's a lot to unpack here. And particularly as it relates to the ways in which state energy offices are grappling with both the challenges and the opportunities to try and meet the associated demand growth in the most efficient and optimized way possible. One thing I'll quickly flag before I pass it to our first speaker is that Tennessee, the State Energy Office, we've been coordinating and having some preliminary conversations with Oak Ridge National Laboratory on this topic. ORNL has received some funding, I believe, from the Office of Electricity for a project titled Modeling the Energy Growth Associated with Data Centers, or MEGA DC. And so this project seeks to explore opportunities to design and develop data centers that aren't just connected to the grid for backup power, but that can serve as a grid cognizant load or a grid orchestrated asset in the most ideal sense. And so through this project, ORNL is providing technical assistance to a number of states. I believe 8 states have signed up, including Virginia and Oregon, and Tennessee intends to work on the project as well. And so I was asked by ORNL to flag this as an opportunity in case other states are interested in receiving this technical assistance. I'm happy to provide information to NASEO to share with the other states on that. But without further ado, I'm excited to hand it over to our incredible lineup of subject matter experts on this topic to share some of their insights with us today. And so I will pass it first to Karsten Baumann from Schneider Electric. So Karsten, I believe you should be able to share your screen. Take it away.
Yeah, excuse me. Can you see my screen already?
Is it the innovation slide?
Yes.
Yes.
Solutions
Yeah.
for data centers and AI. Awesome. Very good. Well, good morning, good afternoon. I really appreciate being here. Alexa basically just said it all. So there's really no need for me to continue this dialogue right now. However, I believe we're in an incredible, exciting times right now. Let me turn my camera on. Can I do this? I don't know where my camera is. Here we go. All right, so I guess now you can actually see me as well. So yeah, we are in an exciting time, and so I just want to give you a brief overview here in what data center means for the infrastructure, for our opportunities, possibilities, and this is formed based on the day-to-day conversations we are having with our customers. And before I go there, I just want to a few words, on Schneider Electric itself, who we are. So we're a Fortune 500 company. We have in the United States about 20,000 employees. We have invested over $440 million between 2020 and 2024, in terms of like manufacturing capabilities and so forth. So we have multiple manufacturing facilities, have innovation hubs and so forth. So Schneider Electric is a big company, and we service all of the data center industry, from the hyperscalers to enterprise, down to edge applications, telecommunications providers, and so forth. So they come in all sorts of forms and shapes and technology implementations and so forth. When we think about the data center of the future and what the data center will be, it will become more digital, more efficient, more resilient, more sustainable, more adaptable, and also it will become and has to become a member of the community. And there's multiple things that can be done in order to facilitate and to promote this actually. So we'll go a little bit into more details about this. When we think about the data center of the future, we have like three main challenges that need to be overcome. Number one, the innovation acceleration is happening tremendously right now. I mean, you can open the news and you read it in the New York Times or the Washington Post or anybody else, that the data centers are exploding. They're consuming more and more energy. Whether that is good or bad, that's a different story. And yet, we simply right now seem to be not able to build it fast enough. And the challenging part is that the innovation over the last 10, 15 years was a gradual kind of acceleration, of innovation. However, in the last 2 years, since the announcement of ChatGPT, the development of AI data centers and all the challenges associated with that, has fundamentally accelerated and keeps accelerating like a hockey stick, which is really challenging because how do we build infrastructure which is there to, serve us for 15, 20, 25 years, while innovation cycles, specifically as it relates to IT technology, is growing much, much, much faster. And then we have a resource shortage. And when I think about resources, it's like threefold. Number one, we already don't have enough qualified people to design, build, maintain, and operate the data centers as who they are today, let alone all the new capacity that's planning to come online in the next 5 to 10 years. Number two, there is simply not enough power, but that's a question, so we will post this for a little bit later. And then thirdly, the general supply challenges we have. So all the equipment we build and manufacture, not only Schneider, but all of our peers in the industry, we simply seem to be not able to deliver it fast enough. And then lastly, whatever we design, build, and then maintain and operate, it has an environmental impact. And we have to consider, how can we build a data center that's not using water, that is not using or emitting any kind of carbon and kind of other particulate matters and so forth. So it has to become a more sustainable environment and build. So in order to protect, our planet and the future for our generations to come. When we look at the overall state, and by the way, this is not just unique for the United States, it's happening almost everywhere around the globe. So we see a power quality, quantity, the sustainability challenge in terms of the emissions, and also a cost challenge. Power is not going to become cheaper. We don't seem to have enough. The quality of the power is not necessarily getting better. With all the intermittent resources like wind and solar coming online, there are more fluctuations, and data center customers need to protect themselves against that. When we look, and this is, by the way, this is from 2022, when we look at the data center market itself, it's expected, to grow about 10% on an annual basis, compounded annual growth rate. And this is a McKinsey report from 2022, and there's others now where actually it's been revised. It's going to probably in the United States grow more than 15% on an annual basis. So this is an enormous amount of new capacity that's coming online, and we have to figure out somehow, where are we going to build it, how are we going to build it, and how are we going to operate it. The data centers themselves, and this is the interesting part, why this is all in the news right now, because 10 years ago, nobody really outside of the data center industry themselves was reading about it because we were just not taking so much energy, right? But now with these hyperscalers, the Googles, the Amazons, the Facebooks, the Metas, and so forth, we are developing data centers, which are now 0.5 gigawatt, 1 gigawatt, or even larger, so they are being designed right now and they're coming online, in the years to come with all sorts of challenges associated with that. When we look at the power consumption, globally, depending on which research information you're going to read and trust, so the data centers consume around 2 to 4% of the global energy. However, it's been projected that by the end of this decade, by 2030, in the United States, data centers may consume up to 10% of the US energy. And when you look at the right-hand side right now, these are the top 10 markets in the United States. Obviously, Northern Virginia, the data center alley, with the largest kind of congregation and association with data center capacity. And then these are the markets. However, we do see that because of the challenges we have in certain areas, data centers start to bring their own power. Alexa just mentioned it earlier, right? On-site power generation in certain forms. And Meta is not just the only one. So we talk to our data center customers on a daily basis. And I specifically, that's one of my roles, help our customers to solve some of those challenges in terms of bringing power, self-generation on-site in a sustainable and environmentally friendly kind of way. And then, for about 2 years now, I was talking about why are we concerning ourselves so much with bringing the power to where the data center is, instead of like, why are we not putting or bringing the data center to where the power is? Because there's plenty of generation. However, there's a lot of constraints around transmission and distribution. And we see this now where data center customers previously would have never considered secondary and tertiary kind of markets, but now because of those challenges, they're actually moving into those other markets. And depending on what the IT application is, you do not have to be in the Bay Area. You do not have to be in Texas. You do not have to be in Northern Virginia. So there's other applications and regions and locations where you actually can bring the data center to where the power is, and therefore solve quite a few of those challenges we have right now. Now, Alexa also mentioned AI has really fundamentally changed and shifted everything, and it's just accelerating. So we think that by 2030, 60% of all the new data center that's being developed is somehow associated with AI, whether this is for training, whether this is for inference. And then what happens with that, the power density, how much power per square foot I need is, 10x, 20x to, let's say, an AWS data center for cloud services we all use. However, not everything is AI. So there's a lot of new capacity still coming online in the more traditional sense. So that's what you see here in these kind of graphs. However, even at Schneider Electric, we have on the right-hand side, we have revised our own projections in terms of all the supply, the capacities, the materials, and whatever the workforce we need in order to kind of supply that. So you see on the right-hand side, the lower green line, this was our projection in 2023 in terms of capacity growth by till the end of the decade. The little green one in the middle, that is by the International Energy Agency, their projections. And we have now, that's the white line, we have actually changed our forecast in terms of what this all will be. So the power density and compute is all at the heart of all of it. And when we look at, for example, the NVIDIA, right now we're deploying these Blackwell chips, and you see that kind of green curve here, accelerating in terms of how much compute power is available in a very small footprint. However, that's not the latest. That's just what's being deployed right now in massive amount. And the next one is the Rubin and the Rubin Next, because we're no longer just talking about generative AI, but we're also talking about agentic AI, which is actually reasoning, which requires more compute power. And that's what I talk about, this innovation challenge. How do we bring enough power and cooling into the infrastructure in order to support all of that? So that's where we welcome ourselves into this new area of the data center, where we talk about connecting the grid to the chip, so making the power available to the actually compute where it's necessary to perform its task. And then with this massive amount of compute, it creates as well an enormous amount of heat. And this heat needs to be extracted out of the data center. And how do we connect this to the chiller? And then Europe, in my opinion, I was born and raised over there, has a lot of technologies that actually allow us to use waste heat from different industrial processes, including data centers, for other purposes, whether it's district heating, farming, and there's certain projects available. And I think we in the United States, we have to creatively think about it. How can we co-locate not necessarily data centers with power, but also co-locate other industries that could benefit from, in this case, the waste heat coming out of a data center, how this could be repurposed. So when we look from a grid to chips perspective, without going into all these technical kind of things, but we have transformers to connect to the grid, then we have this power distribution, the switch gear with all the breakers, similar to what you have in your house, but just, for the breakers and the power. However, just think about it significantly bigger, right? In order to provide all the power into the right areas and to bring this in there, including like UPS, uninterrupted power supplies to accommodate, for any kind of disturbances that happens on the grid. So to not kind of interrupt the processing power itself. And now with AI, we're actually seeing that it's not so much that the power can go out. These AI training sessions, they happen like in 7 minutes interval, and then they ramp down, and then they go like, in saving and data validation mode. However, if you do not continue to cool those chips, these chips, they can literally physically crack and destroy themselves. So therefore, there's different architectures right now where we have to put the cooling mechanism as well on these uninterrupted power supplies. And then when we look at, how do we extract it all out of it, chip to the chiller, and a lot of things we see right now where the traditional air-cooled data center, where literally cooler air, which by the way, 10 years ago, when you walked into a data center, you needed a jacket because it was so cold. And the industry has learned, wait a minute, we don't need to provide 60-degree or 58-degree kind of air into the data center. We can actually provide 75 or 78 degrees air. The chips are totally fine with that. What they don't like is, when the temperature goes up and down really quickly. But we can provide higher temperature into a data center, which then allows us to use economizers so we can take advantage of the free air cooling we have outside and the temperatures. However, with these AI loads, there's so much power in such a small space, we cannot push enough air through this in order to remove the heat from those chips. So therefore, we have to deploy liquid cooling, and they make it more efficient and more because the energy transfer between a heatsink and water in this case, is much more effective than actually using air. We, Schneider Electric, we're working together. One of the big one, of course, is NVIDIA, and we have created this in collaboration with them, like reference designs, where we actually help our customers look. This is what a data center can look like. This is what the power architecture may look like, the cooling architecture may look like, and here's the operation and all the elements you need to consider in order to design this properly. And our customers find this extremely helpful. Not that ultimately you will design and build and operate a data center exactly the way the reference design has been outlined, laid it out here. However, it serves as an excellent starting point, to move us forward, to make quicker decisions, more educated decisions, less iterations, and therefore ultimately becoming more cost effective. And then when we look at these energy strategies for AI, we have to look at the energy procurement. Where do we buy the energy from? Where is the energy we buying, or how is the energy we're buying being produced? Is it coming from a renewable resource? Is it coming from burning coal? I mean, I live in Colorado, south of Denver, and when I drive up to Denver next to the railroad track, I see massive, massive amount of coal coming from Wyoming down to southern part of Colorado, and they burn it, in order to provide the energy we need. So therefore, we have to look at the procurement strategy, and most of the data centers, including the hyperscalers, have fully committed to being powered by 100% renewable energy. It does not necessarily mean that this wind farm is directly next to the data center. However, we do see those environments where data centers are moving closer to, let's say, a solar farm or a wind farm in order to take advantage of that without these constraints about the power distribution and the power transmission. So we have to ask ourselves about the prime power. Do we have enough power? Is it bridging power? So where a data center operator wants to have 100, whatever 100 is, or maybe, let's say megawatt, but the utility company can only give them 20. So how do I make up the 80 today? However, tomorrow the utility company may say, look, we're upgrading our infrastructure, and now we can, instead of delivering 20, we can deliver 40. So now I had to fill a gap of 80, but tomorrow the gap's only 60, then it might be 40, then it might be 20. So we have to think about these creative kind of strategies, and that feeds right into the backup power strategy. Microsoft a couple of years ago made an announcement that by 2030, they will eliminate their dependency on diesel backup generators. It's said very easily. It's significantly harder to do. So we have to look at the prime power and the gap power and the backup power strategies. And there's new companies out there. We have a partnership with Mainspring, a linear generator out of the Bay Area. Fantastic technology, And then we're going to solve for the available power. And how do we ultimately, do this all in a sustainable and in a more responsible kind of way? The future of the data center, I think, will have these 5 fundamental pillars. And yes, sustainable, efficient, resilient, and we continue working and pushing the envelope to become more energy efficient, to become more resilient, in order to provide those services necessary for our customers. However, I also believe that or not me just only, but the industry really, the data centers, they have to become more adaptive. So that means instead of just becoming an off-taker of utility power, but can we become grid interactive, and can we take advantage of self-generation? Sometimes we produce power so we can feed it back into the grid, or we can take our load off of the grid, so therefore less constraints on the grid themselves and more power available to the adjacent residents, industrial, commercial applications. And from an adaptability, so we have to accommodate these new technologies. And I think that's a fundamental aspect, how can we work together? And of course, theoretically, it's all possible. But there's a lot of tools, and this is what I meant early on about the data center of the future will become more digital. So we have to use more digital tools, software tools, which ironically the software runs and has been developed in a data center, to actually become more efficient, to manage and operate those applications, including using AI software algorithm technologies to more efficiently operate the data center, to consume less energy, to become more sustainable, with the constraint of the human resource we have, the capital, by not having sufficient workforce, to actually operate the data centers today, and certainly not the one in the future. So we will see more software tools becoming more digital. So this is what's going to happen. So my key takeaway points here, the next generation of the data center will be, as I just mentioned, more digital, more efficient, more resilient, and accepting new innovations in terms of this chip power growth, and the demand they all have. Co-locating data centers with power generation sites, is becoming more important. And we have to look at how do we, in those cases where we do not have enough power, bring clean on-site power generation to us in order to solve some of those transmission and distribution grid challenges we have. I believe from a legislation's perspective, we can do a much better job by fostering an environment in which the interdependency between the data center and the utility company becomes more attractive in terms of demand response programs, incentives, the interconnection agreements to connect data center capacity to the grid is becoming a big challenge. And I think we can collectively do better. So where then the data center becomes actually an asset to the community, including not only from a tax revenues perspective, but also from a power perspective, and not just simply consuming everything. So there's a lot of things we can do. And we at Schneider Electric, we are your partner here for digitization, the efficiency, and to support the growth in your geographical region, wherever you might be. And with that, I think that's it. My contact information is here. And I really appreciate, and I'm not quite sure how I was on time, but hopefully that all worked out.
Thank you so much, Carsten. That was great. We'll hold questions till the end, so I will pass it next to our speaker from EPRI, Anuja Ratnayake. Hopefully I pronounced that correctly.
You did great, Alexa.
Thank you.
Will somebody? Oh, perfect. All right. I see my slides as well. Carsten, that was fantastic. I feel a little inadequate with my slides after listening to you. So everybody, forgive me if my slides are not as up to par as Carsten's, but I'm gonna really chat with you all today from the perspective of flexibility or load flexibility in specific related to data centers. So between Alex and Carsten, you all set up the background perfectly as to why we are talking about the challenge and the opportunity related to data center growth from the utility perspective or the energy perspective today. Carsten did a fantastic job setting up both the time dimension mismatch as well as the uncertainty because the world of data centers are changing. The world that we knew of data centers for the last 2 decades were smaller scale with specific types of workloads that are familiar to us. The future from here to the next 10 years is a completely different type of a workload with technology that's innovating as we speak to accommodate that workload's goals. And then the size of the data centers that used to be in hundreds of megawatts at the larger scale is turning into gigawatt scale single point loads. That was the backdrop for when we were beginning to do research into the data center industry within EPRI. What we figured out very quickly was this mismatch in timing is going to be a real constraint for both for the AI industry to develop as it needs, and from a setting expectations point of view for the utility industry, the energy industry to rise up and rise up to the challenge from the data centers. So within that backdrop, we began the initiative around DC Flex. In the next slide, you'll see sort of what the DC Flex intent is. There are many things to address within data centers and the next evolution of data centers. Carsten did a fantastic job addressing many of those parts. DC Flex is really focused on one particular element here. That particular element is how do we overcome the mismatch in timing between the data center expectations and utilities' ability to serve those expectations. So the data center expectation, data center as an industry expectation, we've heard continuously that they would like to be up and running within a 2 to 3 year time window for these data centers that are becoming larger and larger. When you think about the energy industry's ability to serve a load that is over about 500 megawatts generally, not to mention the multiple gigawatt scale, requires just about everywhere in the US, it requires new significant investments. Those investments generally go between 2 parts of the grid. One is the transmission grid, the second part is the generation side. Normally, a brand new transmission upgrade is in the range of about 7 years. Generation up and new additions can be anywhere between 4 to 10 plus years, depending on the type of new generation we want to build. So, for example, combined cycle facilities used to be about 4 years. In the new supply chain constrained world, that number has changed. But if you wanted to have a multi gigawatt nuclear facility, we were talking about more than a decade easily. So when you match these two industry expectations, right, the traditional utility industry requires anywhere between 7 to 10 plus years to accommodate a new load that is in the 500 megawatt plus range. Data center industry would like to be connected and fully functional within 2 to 3 year window. This mismatch is the primary reason DC Flex came to be. When we looked at the reason for the mismatch in the timing here, it is driven by the need for energy in about a 15-day window in a year. So it's not for 365 days or 8,760 hours that we need the load to be flexible. We need the load to have flexibility for about a 300-hour window if the location they're trying to put in has particularly a generation constraint. So in normal terms, when you think about the energy grid, we talk about our peak periods and super peak periods. These 300 hours generally fit within that peak period. The intention with DC Flex was to explore whether data centers, particularly this new generation of data centers, has the ability to be flexible during this short window of time that it is required, the flexibility is needed for the grid in order to accommodate the 2 to 3 year window interconnection timing data centers were looking for. So with that in the back of our mind, we came into the research portfolio here, thinking of data centers. Some of this will probably sound very familiar to everybody. Anybody who's been in the utility side, the grid side of the conversation in the last 30 to 40, 50 years, we've all talked about demand response programs. This sounds a lot like a demand response program. The only thing that I tend not to use the word demand response because I want us to think a little bit more expansively about the flexibility potential. So within data centers, we say there is flexibility potential in 3 different buckets. The primary workload, which is the computational workload of a data center, has the potential to have flexibility. Figuring out the depth of that flexibility is really is one of the big elements within DC Flex. But beyond the primary workload, a data center also has a significant amount of auxiliary power needs. When you think of a data center's total power needs, primary workload can be anywhere between 60 to 80%, with auxiliary power being the majority of the rest. And cooling tend to be about 10% of that total auxiliary power. Total load, 10% of the total load, most of the auxiliary power is concentrated in the cooling. That cooling load has the potential to be flexible as well. We can talk a lot about does that cooling load flexibility potential exist if it continues to be air cooling, because air cooling has been what data centers have used for the last 20 some years, and the industry has done a lot of work to become more efficient with air cooling. But air cooling is not the end all right now, given the multiple other newer technologies that are being explored. Everything from liquid cooling to geothermal solutions are being explored within there. So that's the second set of flexibility potential. The auxiliary power, particularly cooling loads, potential to be flexible as it is needed back to the grid. The third piece is this backup solution. Carsten mentioned this. There are different wording that are being used today, from backup to bridge power, etc. But traditionally, 95% of total data centers carry some form of backup generation. majority of the backup generation up to this point has been tier 2 diesels, which have very limited value as a grid resource, because essentially a tier 2 diesel in most jurisdictions cannot operate when the grid is still up and running. But the fact that we the data center industry is spending money to have a backup solution opens the door for us to think about the backup solution as a flexibility option. Carsten mentioned Mainspring, one of the linear generator companies. Their emission footprint is very different. We are doing some of the testing with the backup solutions to see, can we do a drop-in fuel that can go in the same engines, but potentially be like hydrogenated vegetable oil. Would that change the emissions footprint adequately enough to make the backup solutions a truly viable portion of that flexibility, the 3 flexibility elements? Now, there is also all of the technologies that are completely different from diesel gensets and even gas gensets, everything that goes up to energy storage solutions and other types of generation solutions. They're all part of the mix. So we think of the flexibility portion from these 3 buckets. And the idea ultimately with DC Flex is to try and understand, in combination, can these 3 elements of flexibility offer a flexible large load that can then work as a grid resource instead of being a passive load that requires 5 nines reliability as we've had them be traditionally. With all this in the back of our minds, we've structured the project to have 3 work streams. The first one is really looking at the data center design side. Carsten mentioned some of the reference architecture that they've been working on. Similarly, what we are really trying to get out of this work stream one holistically is, what is the reference architecture that we can offer to the data center industry, to the point that the data center industry would be able to understand the requirements of being a grid resource and how to incorporate that into their day-to-day practices, both on the design side as well as on the operation side. Workstream 2 is looking at the same element, but from the other side, sort of the other side of the coin. If we had data centers that had the ability to be a flexible grid resource, what kind of programs would enable us to capture the highest value from that available flexibility? And how do we ensure it is both sticky for the data center customers, but also equitable for the rest of society that would be sort of benefiting and bearing the cost with the new investments that's coming? Then workstream 3 is really focused largely on the utility side, to help the utilities to go on this journey of how to incorporate flexible large loads into midterm and long-term planning processes. So many of you who understand utility planning very well probably think of demand response programs as either a peak solution only, or energy efficiency programs as a net reduction in the required load to serve. What we are trying to do with Workstream 3 is try to develop the tool sets, processes, and practices necessary to be able to consider flexible large loads as a peer to any other resource type. So these would be dispatched the same way with the same intelligence as a traditional resource. What are the tools necessary to do this? Within Workstream 3, we also are addressing things like interconnection processes and how to consider flexible loads as opposed to passive loads in the interconnection process. We are working closely with NERC and the NERC Large Load Task Force, as well as a number of other industry forums to get this through. So this is sort of the quick snapshot of DC Flex. What you're not seeing here that we are going to introduce soon is a work stream that is focused on the energy supply side. You heard briefly about the different the changes in the profile of the load itself. In our work stream, 3 early deliverables around how to forecast the data center load in each jurisdiction in such a way that the uh, build plans are accommodating the needs. One of the things we found very quickly was the profile, the energy consumption pattern of data centers when they're AI data centers in particular. They are significantly different from anything we've seen from data centers before. In the back of my mind, every time I see that profile, I keep thinking this is more of a steel mill profile than the traditional flat load data center profile that we are used to. What that means is when we think about what energy supply needs to look like from the grid perspective, from the utility perspective, that energy supply also has to take into consideration the nuances of this profile. So addressing some of that is a new work stream we are adding into the DC Flex space that you're not seeing here in the quick snapshot. I'm going to quickly go into the next slide and wrap up here very shortly. In the next slide, you're really going to see the current membership that is coming together to collaborate on this flexibility element. This page is a little bit old right now. I think there is about 38 folks that are covered on this page. We are at about 41 or 42 members right now. The membership is very lucky to have a fully engaged multiple industries coming together to work on this. So the membership piece keeps changing to the point that this page keeps getting updated rather often. And then I'm going to close the whole my portion here with one last slide. It's actually a slide that gives you access to a number of publicly available research from EPRI that is related to data centers. Many of these were the research that led us to creating DC Flex. So wanted to make sure you have access to that, but if you come across anything else that that you can't get access, or you just want to catch up after the fact about any of these, happy to do that as well. Alexa, with that, I think I will hand it back to you.
Thank you so much, Anuja. Lots to think about and digest there. So I will now pass it to our third speaker, Hillary Pearson with Line Vision.
Great. Thank you so much, NASEO, for having this discussion. Alexa, Karsten, and Anuja, it's wonderful to be here with you all today. It's always tough to go last because you all covered some really great points. But Line Vision, we are a grid enhancing technology company based in Boston. GETs are hardware and software tools that can be put onto existing or new transmission assets to help increase their capacity and enhance their efficiency and overall safety. So if we can go to the next slide, please. So I wanted to just kind of kick off my comments by...
Sorry to interrupt, but we do not see the slides. Oh, my apologies. There they are. Thank you.
Okay. Okay. Because I can see them. Glad it's confirmed everyone else can. So I wanted to just kick off my comments by level setting a bit around a critical issue as we talk about data centers and artificial intelligence generally, which is access to electrons and the critical role of grid capacity to facilitate the flow of those electrons, which power up the data centers that are home to the energy intensive servers that ultimately help to provide the computing power, the computing resources that are necessary to train and deploy AI models, which, as we heard today, continue to further advance and refine and change. So as we know, there are a variety of reports and projections related to data center load growth. One of the latest reports looking at the nexus between AI and energy is from the International Energy Agency, which found that electricity grids are already under strain in many places, including the US. And they estimate that unless these risks are addressed, around 20% of planned data center projects could be at risk of delays. And the issue of timing is really important, as in order to connect to the grid and operate, large loads like data centers need transmission capacity. And traditionally, large loads have been able to interconnect without necessarily, scarcity in mind. Utilities have been able, they react to service requests and to load letters, and the grid has had time to adjusting these loads. As if you think about, traditionally buildings, apartment buildings, for example, they might take time to reach full occupancy. Factories tend to scale up over time, but these power intensive data centers are different. Their very intensive power demands need to be met from day one. And unlike residential homes or 9-to-5 businesses, these are facilities that generally operate 24/7. So while the growth in electricity demand unleashed by artificial intelligence has really become a critical issue in energy and grid planning, what is certain is that the already limited capacity of the transmission grid to support new loads will be increasingly strained by this growing amount of 24/7 demand. I think, as we heard, the development timeline for data centers, these are facilities that can be built and connected to the grid in a fraction of the amount of time that it takes to build new transmission infrastructure, which again tends to be in the 7 to 10 year time horizon. So I think a key question really is, do we have the infrastructure in place to help meet that demand? And on the transmission side, it's not looking very encouraging. For example, the US installed about 1,700 miles of new high voltage transmission per year on average in the first half of the 2010s, but that number dropped to about 645 miles per year on average in the second half of that decade. And in 2023, that number decreased all the way to 55 miles of new high voltage transmission being built in the US. In the meanwhile, there are constraints on the grid that are resulting in increasing congestion costs, and these are costs that do ultimately trickle down to the retail customer bill. So really, our country's geopolitical standing, our overall economic competitiveness is really linked to being able to both serve these large loads, like data centers, while maintaining affordable, reliable service for all other consumers. So while we know the timely connection of data centers is critical to the advancements of AI, it's therefore critical to look at what can be done to create transmission capacity quickly. Next slide, please. So, what's exciting is that there are a growing number of tools available to help meet increased data center demand. And I think the role of dynamic line ratings in particular is critical, given its ability to bolster transmission capacity by as much as 40%. That's a significant jump that can help to energize more load on the grid now. So what is dynamic line ratings? This is technology that monitors ambient conditions that help to heat or cool transmission lines to help to calculate their true capacity based on thermal limits. So by factoring in these local real-time ambient conditions, particularly in regards to wind speed, dynamic line ratings can identify times when there's additional ampacity available on a line that would thus, allow an increase in current and therefore more power to flow across a line. There are ampacity limits on transmission lines because of the thermal properties of the conductor or of the line itself. So if a conductor is overloaded, it can overheat, it can exceed its maximum operating temperature, that can potentially result in line failure. And because of this risk, utilities have traditionally applied a static rating for a line, meaning a fixed amount of current that can flow through the line based on static, unchanging, and often conservative assumptions. So technology solutions like sensor-based dynamic line ratings can help to validate utility assumptions about their line ratings with field-based data, ultimately helping to ensure that lines are optimized and operated safely and reliably. So we at Line Vision feel that dynamic line ratings presents a timely solution given that much of this new AI-backed data center load is looking to connect to the grid, in the next 2 to 3 years. So in the near term, dynamic line ratings can be deployed to help meet some of that gap in transmission capacity until new transmission can be built. Also thereafter, by enhancing the capacity of new transmission investments, as the deployment time for dynamic line ratings is a mere months. This is not years or decades, and it can be done without the need to incur an outage on the system. So at LineVision, our non-contact sensor and software platform actively monitors transmission lines, and it provides critical data that utility can use to increase the capacity on their existing network by way of dynamic line ratings, as well as to enhance situational awareness capabilities, as well as using digital twin models to better understand asset health. So having that data that comes from continuous monitoring is critically important to not only determining where we can safely put more power through existing lines, but also helping to close a visibility gap that exists on the transmission system as well. Generation stations and substations are heavily monitored. Those lines leaving those facilities that really make up the backbone of the electric grid are, for the most part, not continuously monitored today. So, lastly, right as we need the grid more than ever to help fuel these data centers, support manufacturing, electrification, more and more of its components are reaching the end of useful life. So about 70% of transmission lines in the US are over 25 years old and approaching the end of their typical life cycle. But at LineVision, we've installed on lines that are pushing 100 years old. So having data to help operators better understand asset health, using data from the field to help determine, when a line might need to be reconductored, or how might preventative maintenance strategies need to be addressed based on how a line is behaving or positioned out in the field. This is all really key to helping utilities optimize their assets and enhance operational efficiency. Next slide, please. So at LineVision, we're proud to have done over 400 deployments across 3 continents. This is a slide that highlights some of our recent projects. And if I had to paraphrase reasons for interest in this technology, I think it's a few key things. One is the issue of load growth. What tools can I use to help me, if I'm speaking as a utility, help me to move quickly to serve that load growth, see that critical economic development come into the service territory, come into the state, I think is definitely a reason for interest in the use of DLR. Second is, I think, reliability and resilience. So getting data from the field to help better understand how these critical assets are behaving, how they're positioned out in the field. I think another, we think about the risks from wildfires, for example. Another critical, data set that becomes available is getting highly localized wind speed information. Being able to understand what winds are looking like in the existing corridor, in the existing right of way. And then, last, recognizing that grid enhancing technologies, dynamic line ratings very much are an and solution to building new transmission, but that building new transmission tends to come with, a lengthy timeline. I think there's interest in using tools that help to demonstrate that existing assets are being used to their fullest potential, and that, tools are being used to squeeze the most out of what exists as utilities also look to build new infrastructure. So as you can see, some of the percentages noted on this slide, just to help contextualize what that means, there was a study done in Texas over 15 years ago that found that just a 10% increase in capacity on a line is enough to eliminate virtually all congestion on that line. And when you're able to eliminate that congestion, it just creates that much more headroom for electrons to flow, again, depending on the season. Next slide, please. So, it was great to hear some of the previous speakers mention, this theme and opportunity with flexibility. As we think about the build out of data centers, when these facilities are built, there are significant costs that can be associated with that. So facilities often will need new generation, the accompanying grid infrastructure potentially including new or upgraded transmission and distribution lines, substation upgrades as well. And these are costs that are likely to be socialized or passed on to other customer classes. So using things like grid enhancing technologies can be a key way to help address these costs by ensuring that the existing infrastructure is being used to its maximum capabilities. It ultimately just reflects what is a pretty consumer-friendly notion of using what you have most efficiently to its maximum capability before you look to buy or build something new. And so in addition to the additional headroom or capacity that grid enhancing technologies like DLR can create, as is noted here from a study that looked in the PJM footprint, it's also exciting to think about how these large loads themselves can be a bit more flexible. There was a great study released earlier this year showing how load flexibility, or this idea of temporary reductions in electricity consumption during peak demand, having these loads occasionally cut or shift their power when the grid is kind of most stressed, could help to further enable economic growth while maintaining grid reliability and affordability. So in the theme of kind of looking at all tools in the toolbox, how to be more flexible to move fast, if I'm a utility looking to serve a new data center and that new load requires new infrastructure, well, again, in the transmission space where new lines can be in the 5 to 7 to 10-year range, and that timeline not necessarily aligning with what the customer wants, how can I use a tool like dynamic line ratings to get more power through existing lines to serve that load? The customer, in this case, the data center, can perhaps use on-site generation or storage, or simply look to flex or shift their load to help backfill when at times when that capacity is not available. So along the theme of flexibility and innovation in addressing these costs, we have seen utilities working in partnership with large C&I customers, including hyperscalers, on proposed tariff structures. So for example, Duke announced that it's working with some large C&I customers on proposing clean energy tariffs to support financing options for emerging technologies. And the Nevada Commission recently approved NV Energy's Clean Transition Tariff, which is a framework that was developed in partnership with Google that will allow the utilities' existing large load customers to receive power from new clean energy resources. So while our energy system, it's built to handle the extreme demands of the hottest summer days, the coldest winter nights, it is often underutilized. And so I think it's critical to use tools like grid enhancing technologies, strategies like load flexibility, ultimately to help manage these peak demand hours and ensure that we're getting the most out of the existing grid, particularly as we look to deploy timely solutions and investments that help us to maintain global leadership in AI. Next slide, please. So, I think federal and state policymakers, have a number of priorities to balance when it comes to the growth of data centers and large electrified loads in general. These priorities include fostering an environment to support economic growth, but also keeping energy costs affordable for all customers, and as well as maintaining a safe and reliable transmission and distribution grid. Some state energy offices are also tasked with putting states on the path to achieving clean energy goals. So in line with these priorities, there has been a growing interest in states to look to make sure that these technologies are studied and evaluated in their specific state processes. So while this is not an exhaustive list, it does help to showcase what some states have been up to regarding grid enhancing technologies. And just last fall, the NARUC, the National Association of Regulatory Utility Commissioners, they did pass a resolution highlighting how both GETs as well as high performance conductors help to save customers money and improve reliability. So I think that's the end of my time. Just appreciate being here and looking forward to the discussion and answering the questions.
Thank you so much, Hillary. Awesome. So I'm going to kick us off with a question, but for folks who are on the line, if you have questions for our speakers, feel free to type those in the chat and I'll get to those in a second. But to kick off the Q&A, I'll start with a question, knowing that our audience here is state energy offices. I think, Hillary, you were just touching on this a little bit, but curious to hear from you all. Where do you see the role of state energy offices, particularly in the development or use of the innovative tools that are kind of focused on data centers and maximizing the efficiency and optimization of those data centers?
Do you want to hear from all of us?
Sure, go for it.
All right. Well, I think it's, I mean, I mentioned it and Hillary and Anuja as well. I think the load flexibility is a real challenge, right? So, and then the interconnection of connecting the data center to the grid is also a challenge. It takes a long time. And I think what would be really beneficial if we look at, you know, the more attractive legislation can become to facilitate this, the data centers, they would love to be served and connected to the utility, right? However, if it's challenging, not possible, not cost effective, they are currently solving this problem for themselves through self-generation. So which kind of like defeats a little bit this purpose, right? So why do we have the utility? So, and traditionally, a monopoly is not necessarily very helpful to foster innovation. But you know, the data center industry right now figures it out themselves. So, but they would love to be connected to the utility company. So I think legislation can do two things. You know, number one, make it easier to interconnect, and number two, you know, create this. I know, Anuja, you didn't want to use the term demand response. You know, but if I'm able in those peak demand times to simply take large scale data center loads off of the grid, then that power is now available to, you know, C&I customers, residential individuals, and so forth. So incentivize that. That will actually really solve and help to solve these kind of constraints.
Great. Anuja or Hillary, do you have anything to add to that?
Alexa, I think Carsten positioned it really well. From a legislation perspective or regulatory perspectives, I think we need to think of, it's not that I don't like the word demand response. Demand response comes with a predetermined definition. I think what we are looking for in this generation of load flexibility is sort of the evolution of what we traditionally used to call demand response, right? And traditionally, we used to call just the workload flexibility as demand response, and the utility programs would try to figure out the potential of a given technology inside a customer's premise to come up with demand response programs. What we've seen happen working with both the utility industry and the data center industry in this particular effort is data centers, end of the day, the AI evolution applies to like 6 to 10 people. So this is not a market that has thousands of people, and therefore they are willing to look at, say, individual technology inside their four walls and think of demand response as a utility program for that individual piece inside their buildings, right? What we are hearing from the hyperscalers is their workload flexibility is part of their secret sauce. So they don't want anyone to come and create a utility program that's about computational flexibility. What they want from the utility industry is, give me a signal that says, if you operate this way, I can interconnect you faster. So from the regulatory legislative mindset, if we can enable utility programs that would essentially provide that signal with an accurate representation of value, then the data center industry is willing to rise to their challenge, which is to say, I will design my data center, I will operate my data center to be a true grid resource. I think that's the point where we are slightly changing this conversation that we've had for demand response for the last many decades to really hold the load itself responsible. As long as we are thinking of how to enable programs that does this nuanced aspect, we really have a great partner in the data center industry. Carsten,
Yeah,
did I say something that's giving you heartburn?
no, actually, no, absolutely not. And I just want to add one more thing, so um, it's about, for the data center customers and many other operators, it's about managing risk and what's the value, the monetary value, because we have had demand response programs for many, many, many years, right? But if the risk is too high and the reward is too small, the data center customer that, you know what, I'm not participating. So it needs to be the right balance, right? So the risk needs to be managed and mitigated, and it needs to be financially attractive.
I think, I would just throw in, I think another area just where you are seeing, at least from a technology solutions perspective, some changes is just when you think about integrated resource plans, for example. So, an IRP generally is what's the strategy, that utilities will use to help meet, future energy demand. You've got to consider both supply and demand side resources. But this is about, aiming for cost effectiveness, for overall reliability. So I think that, this effort to look to make sure that, as most states do require their utilities to regularly develop IRPs, that at least in regards to grid enhancing technologies, there's now, the possibility to address the use of those technologies in that framework of an IRP, for example.
Great. Thank you. Lots of good food for thought there. All right, so I see one question in the Q&A. It was addressed, or Anuja responded to it, but I will throw this out in case other folks want to chime in on this. Rodney asked, please ask about potential for thermal energy storage or storage of cold or coolness to shift loads and reduce peaks, overcooling off-peak, ice and phase change materials, ground-based geothermal storage. This would be in addition to cooling efficiency improvements.
Yeah, I think generally speaking, energy storage in different forms, including thermal storage, is certainly a viable or can be a viable asset, to help reducing or create greater flexibility, and shift loads, in terms of time of use and so forth. So I definitely see it, but sometimes it's geographically constrained. So it depends on where a data center operator is. However, we do see in terms of site selections, and I do understand there were some other sessions already addressing the kind of site selection process of data centers. It's certainly something that's being evaluated in their site selection process. How can I leverage thermal storage, to actually further improve, my operation and my efficiency?
And Alex, when I responded directly to Rodney, but we've seen some really interesting work. Actually, some of them is being done by DOE's fossil office around the geothermal cold storage potential. Going into it, I had this same concept. The moment somebody says geothermal, my head directly goes to, oh, there is a specific locational need when you are trying to do geothermal. There seems to be certain technologies that are emerging that does not need necessarily the same the cavern concept and the geological formations that we automatically associate with traditional geothermal. So there seems to be new technologies that are emerging. Within DC Flex, we are trying to evaluate the potential of cold UTS, the way DOE is calling it, that as a potential seasonal flexibility element. It's somewhat early in its development, so don't have a lot that I can point to and go, this is a technology that is fully validated and we'll be able to tell you X, Y, Z. But over the next 3 years, as DC Flex happens, that is one of the elements we are trying to understand. The air cooling technology for data centers are at a very high efficiency level. So we do need other options for sort of capturing the most out of the cooling load from a flexibility point of view. And Rodney's point is very valid. The thermal cooling is a good option in addition to the liquid cooling options that many of the data center customers are looking at.
Thank you. Okay, it looks like we've got a question from Kyle. He says, as you've stated, a typical data center load profile is changing drastically from the continuous load profile. How frequent are these changes, and will these bring further challenges to automated responses from a BMS? Immediate responses may lead to mechanical unit hunting and using more energy than necessary. How would you recommend data centers and engineers change to these rapid changes in load?
Yeah, I think it is an interesting observation, and it really depends as well on what is the IT load. So for example, if you have a traditional cloud service data center operation, the load is still relatively flat. Of course, it grows a little bit in the afternoon when it gets warmer. Generally, it's more in the summer times versus the winter times, just because of cooling or additional requirements for cooling. However, when we see these AI loads, that is a incredible complex phenomena right now. So because now you have, it doesn't matter, let's say you have a 50 megawatt AI training cluster, and they all work together in conjunction. They ramp up and down within milliseconds from hardly any load to almost full load, and so there's a huge load fluctuation, which can reflect back onto the grid, and even at times, trips upstream kind of like breakers, and leads to certain kind of outages, which needs to be avoided and needs to be mitigated. So there are certain technologies, super caps, form of energy storage, short-term UPS technology that can actually help to buffer that and not reflecting it back on the grid. But these are significant challenges we see right now. Our customers trying to solve, or actually we're solving it right now. But it's dynamic, and it's depending on the operation. It needs to be understood and then mitigated against it. But it can be done. But yeah, it's interesting.
Anything to add?
I think Carsten did it justice, Alexa, but Kyle, your point is very valid. Part of the DC Flex deliverable set is trying to capture we call it a profiles library, and our intent is it stems from the recognition that the load profile for the data centers are changing. Carsten gave a good number of things to remember there, right? Like the type of workload, there will continue to be data centers that are cloud services data centers. AI data centers that will be inference focused will have a profile that is similar to the cloud services data centers, which is more of that straight line. It's not actual, nothing is actually straight line, but you understand where I'm going. It's the frontier models, the training models. Those are the ones that we are seeing the steel mill profiles. Within DC Flex, we are trying to create a profile library that the utilities in their planning can leverage, so they understand what to expect when they see a new data center coming on, how to map that, and how to have, really, it's the library is intended more to get the conversation started with the data center customers to figure out what do they anticipate their data center use to be. Right now, nowhere in the interconnection process do we ask that question, because this has not been a phenomena that we had to deal with over the last 20 some years that we've had data centers, right? So Kyle, we don't have all the answers, but there is a definite recognition that the profile is changing. There is very early anecdotal data sets that show what the new profile looks like. The utility industry has experience dealing with this kind of profiles. We've just never had this profile being like 20% of our total load, right? So that's the evolution that we have to go through. Hopefully, I'm answering your question, Kyle. If I'm leaving something out, tell us. Happy to chat more.
Great. So I'll ask another question. Can you think of any examples of strategic partnerships that have enabled the development of the use of these types of tools that we're touching on to meet data center demand growth? I guess I'm wondering if there's any case studies specifically or examples of data centers that are, grid cognizant or orchestrated grid assets, or are those still to be developed in the future? Are there any strategic partnerships that are working to develop such that we should keep our eyes on? Just kind of curious if you guys have any insights there.
I
I
think
think,
there
Anuja,
is
you should answer that one, right? I mean, DC Flex really addresses this, and it's a great consortium of industries, and not only off-takers, but generation people and companies and organizations. So I think that's fantastic.
Yeah, Alexa, I think the intent with DC Flex was definitely to address that need. And like many of you who know EPRI, you know that our primary membership is the utilities, the system operators of the world. But DC Flex was intended to break that mold and invite the data centers, the technology providers, the IPPs, like everybody together, because we were looking at the potential challenge is such it needs to bring all of the stakeholders together to address this. Alexa, your specific question about are there projects that have demonstrated the potential of sort of everything we've talked about? There are one-off pilot projects we've seen. Like Google's done a number of projects that you can find on Google's website where they show how they've done spatial flexibility, where when they could not do all the work in a given location, they would move some of that work load to a different data center and still be able to continue the work as they planned, but depending on the grid needs. Google has also done that actually based on the carbon footprint of a given grid. When they wanted to achieve a certain carbon footprint and the grid resources were not aligned, they would move things around. I believe there is a majority of the case studies I've seen that addresses beyond that workload flexibility, the other two elements of flexibility happens. Carsten, you can correct me here, but most of what I've seen has been in like Ireland. So Ireland, because they have quite literally their largest single customer load is data centers, and
Yeah,
a majority
25%. Yeah, 25% of Ireland's energy consumption is being consumed by the data centers. So Ireland is one a good example, or Europe in general, the Nordics, right? So where we have technology to actually inject power back into the grid, so to help stabilizing the grid in terms, it's very short, very fast reacting, highly rewarded financially to stabilize the grid, right? So in terms of voltage and frequency. But
yeah,
most
to
of those are actually in Europe, so.
Yeah.
But to your point, Anuja, you mentioned Google, and then Google is also unique in the sense where they have kind of excess capacity, so they can shift it from one location to another one. If I'm a multi-tenant data center, like let's say Digital Realty, Equinix, the two largest globally, and if I am an enterprise customer and I have my data center assets sitting in their facility, they can't just shift it around, so that's so there's just possibilities, and there's also a lot of restrictions around it.
So for I think Alexa, you were the one who mentioned the XAI facility in Memphis. I think there is a really good case study there to pay attention to because they are potentially the first. Actually, they're not the first. There is a European case study that is ahead of them, but this was the first in the US where the interconnection timing was significantly reduced by having on-site bridge power. There are other nuances that they're working through in getting to be a grid interconnected data center, but there is definitely something to learn there as well from that three legs of the flexibility stool concept. So a few ideas there, like so not comprehensive by any means, but to Carsten's point, this is what DC Flex is trying to do. One of the major elements of DC Flex is having 10 plus real world field demonstrations. We have 3 confirmed and identified. They have not been announced just yet. We'll announce them by the end of this month. Many of them, but our intent is to have about half of those 10 here in the US and the other half around the world, but to test and validate every one of these flexibility elements, as well as to demonstrate the validity of like the programs that we are going to propose as the best in class programs to adopt.
Great. Awesome. Well, thank you guys so much. I want to thank you all for your time today and your expertise on these topics. I think I'm going to pass it back to Cassie to close us out.
Yes, thanks, Alexa. And thanks so much to Carsten and Hillary and Anucha for joining us today. We really